In this video, we are going to discuss about unit impulse signal, and this is useful in signal sense system. It's one of the fundamental signal which is applied in signal sense system. Let us discuss this one and its few applications. Now, to understand the impulse signal, we'll consider two kind of signals. One is continuous signal, other one is discrete signal. And in continuous time signal, this unit impulse signal is denoted as delta symbol, del of t, continuous time, and it is specifically called Dirac delta, okay, and we will discuss discrete version of this one later on. So del of t is defined as it is equals to 0 for t not equal to 0. This is very useful. So when t not equal to 0, everywhere the delta function is 0. This is first one. And to get this unit impulse, we will consider the area under this signal. So del t signal is total area dt. Area under this signal means integration of del of t dt, total minus infinity to infinity, and if it is becoming 1, then only it is called unit impulse. Okay, so this delta t is the unit impulse signal in continuous domain, and it is represented as, we can show in diagram like this. So this is your t axis, this is the amplitude axis. We will show it. So what we will do, as signal is available at t equal to 0 only, and t not equal to 0 everywhere it is absent, but total area is close to 1. Okay, so what we can show, obviously amplitude is going to be very large towards infinity. So at t equal to 0, its amplitude is infinite. That's how we will put a arrow on this y-axis. And except this one, this side is 0, this side also it is 0. So we will put a arrow at that place at t equal to 0. That will indicate it is a del of t. Okay. Now how to get this del of t? This looks like it is impractical, because at t equal to 0, its magnitude is infinite. How is that possible? Right? Now to get this idea, del of t, we can consider some kind of approximate things. Then we can start. Suppose I can consider one signal like this. Suppose this is time axis. I can consider one gate signal. This is one gate signal with this side is suppose minus plus capital T. This is minus capital T. Okay, this is at 0. So this width is 2t. So this width delta equals to 2t. Now to make this area under this graph, so this area, to make it 1, so this height will adjust. So this height, can I make it 1 upon 2t? Because width is 2t and this is 2t and height is 1 upon 2t. So this will cancel and area will become 1. Okay. So to make it 1, we will consider the height is 1 upon 2t. Now if this t is approaching to, is reduced. Okay. Suppose if I reduce it further, if I make it half. Okay. If I make it half, just this thing and this thing only. Okay. It is minus t by 2 to plus t by 2. Then what will happen? I need to increase the height to keep the area, this area equals to 1 again. Again, if I further reduce it, suppose like this, I need to increase, because this width is further reduced. So I need to consider a larger magnitude so that this area will remain 1. So we used to make area remain 1. So we can reduce this t. So t is approaching to 0. That time this height will become infinite, but area will remain 1, and width is becoming close to 0. So delta is going to be 0, the width is going to be 0, and the height is becoming 1, but area under this curve, if I call this is signal xt, so this signal xt dt, it is minus infinity to infinity, this total area will remain 1 all time. So this is the concept of unit impulse. So as t is approaching to 0, so it looks like that its magnitude is going towards infinity, so we will show in this way. So this is your del t signal. So that we can realize from this one. Not only that, we can consider one triangular signal. From there also we can reduce this width and we can get the area 1, and then we can approximate del t signal. Not only that, we can also consider sinc function, many ways we can start with, and we can get close to delta signal. Fine. Now we'll come back here, the discrete signal. In discrete signal, we'll consider the same symbol del, but it's a sequence. We'll put n, delta n. Now here there is no ambiguity. At n equal to 0, it is particularly defined, and that will be 1 at n equals to 0. There is no issue at all, but it is 0 elsewhere for n not equal to 0. Everywhere it is 0. So it is particularly defined, and this kind of delta function is commonly called as Kronecker delta. Kronecker delta. So for discrete sequence, we will use Kronecker delta. For continuous time domain, we will be using Dirac delta. Okay. Now here, this is perfectly fine. So this is your n. It will take integers only. N equal to 0, 1, 2, 3, minus 1, minus 2, all those things. So at n equal to 0, its sample value is 1. I will show in this way. This value is 1, and except this one, everywhere it is 0. Okay. So you can see that this indices, this is at 0, it is 1, 2, 3, this is minus 1, minus 2, like that. Everywhere it is 0, but at 0 only its sample is 1, and it is considered as delta n. Okay, so we will call it del n. Clear? So this is a discrete signal, discrete unit impulse signal called Kronecker delta signal. Now we are going to discuss some properties of these signals, okay, and how it will be useful. So let us start with the discrete one. And suppose if I consider one sequence xn, this is a xn sequence. So how can I write this xn sequence? So it can have certain samples values. So suppose at 0 it is x of 0, and then it can have x of 1, then sample will be x of 2, like that we are considering. And this side it is x of minus 1, like that. So this is the sample at n equals to 0. Is it fine? So I can put this bracket as well. Okay. Right. So this is a discrete sequence. We can show it in graph. Suppose we can have certain graphs, all those things. Right. Suppose, for example, if I consider one graph to show these things. Right. So these are the samples. So at 0 this is the sample, at 1 this is the sample, at 2 this is sample, like that. Some things randomly I am considering. So what is this? This is at 0 instant. This height is nothing but x of 0, and this at 1, this is nothing but x of 1. Okay, and this height is nothing but x of minus 1. So those are the samples, and this side, this is your n, and we are plotting this is x of n. Fine. So now how to represent this one? Already I have said that this only one sample, this one, if it is only there, no other is there, can I write in signal wise, this magnitude is x of 0, but it is located at n equals to 0, so it is, we'll call it del n. Remember that if the sample is here at n0, then this delta function, I'll call it del n minus n0. Okay, so it is located at n equals to n0. There is only one sample, that will be considering del of n minus n0, but its amplitude is different. Its amplitude is x of 0, then it is del of n, and similarly this one I can write x of 1 del of n, like that. Is it okay? So each sample, now it is a combination of all those things. So thus total sequence xn, this sequence xn we can rewrite as, so one sample at n equals to 0, that we can consider here. So it is x of 0, and it is del of n. That is the corresponding signal, and its previous one is after 1. Suppose if I consider it is x of 1, this sample, and it is located at 1, so that's how I will call it del n minus 1. So similarly I can consider the kth sample, it is del n minus k, like that. Similarly previous one, negative side, that also we can consider x of minus 1, and it is del n plus 1, right? So what is this? It is a combination of all the things, all the samples. So in short, we can write all those things, these together, it is nothing but summation from x k, and it is del n minus k, and k will vary from minus infinity to infinity. So you can see that any sequence we can represent in terms of only delta k, combination of delta k. This is very, very useful concept. So what I am saying that any sequence xn we can write as a combination of del n minus k, and these samples are nothing but x of k. Okay, so this is useful. K will vary from minus infinity to infinity, and this formation meaning is that we can think of any sequence as a combination of only impulses, and this will be useful to understand the convolution for LTI system. So we'll discuss convolution for LTI system, linear time invariant system, and there it will be useful. A similar version of this one for continuous domain, what you will get? You will get x of t, we can write similarly, x of t, this summation should be replaced by integration, and this is your x, and this k is replaced by another known variable tau, so it is again delta, and this is your t minus tau, and this is minus infinity to plus infinity. Tau will vary from minus infinity, and this is integrated with respect to tau. And this is the for continuous time domain, and we will be using this signal, this representation, to get its impulse response and correspondingly the convolution. Okay, so we'll discuss all those things, what is the meaning of impulse response, to define these things. But before that, some particular properties we'll be discussing. So what is the property of this signal? So some properties. So first one we can consider, if any function f of t is multiplied with del of t, what we can write? That simply we can write, it is nothing but f of 0 times del t. Why it is so? If I consider one signal, this is one signal, that is your f of t. Now this signal is multiplied with another signal, that is your delta function, and delta function, you know that it is located at 0 only. So this is the delta function del t. So if I multiply element wise, obviously you can see that everywhere it will be 0. So resulting things, this form will be almost del t only, but that time this value is f of 0, this height, that should be multiplied with del of t. So that's how it will remain del of t, because otherwise it is absolutely 0. Because anything is 0 is multiplied, it will become 0. So its nature will be like an impulse, but at that moment at t equal to 0, its value is multiplied by f of 0. Thus it will be f of 0 and it will remain the function del of t. So this shape is lost because this value is entirely 0 everywhere. If you multiply, everything will be 0. Okay. So after multiplication, only you will be getting some like of impulses like that, and that time this f of 0 is multiplied at t equal to 0. That's simple. So if it is other places like f of t, if it is located at another place capital T, that time what I can consider? Obviously it will be located in different places. Suppose if it is located here, this is del t minus capital T, it is located at capital T. So that sample only it will choose this sample. So this is nothing but f of capital T. This is multiplied with this function. So I can write f of capital T, and it will remain del function located at capital T, means t minus capital T. This is very, very useful concept. Now third one, if I integrate these things, f of t and del of t minus capital T and dt from entire range, what we will get? We will get only this f of t. Now be careful about these two. It is very, very useful concept. So why it is so? So already I have said that these things I can first write as integration minus infinity to infinity. I can replace this product by only f of capital T and then del of t minus capital T dt. So these things I am replacing only f of capital T. Now f of capital T is constant, independent of capital T. So that I can take outside f of capital T, and it is nothing but integration of del of t minus capital T dt and minus infinity to infinity. And you know that the area under impulse signal, it's a unit impulse, that's why its area is always 1. This area is always 1. So ft equals to ft times 1 is nothing but f of t. So this property is very useful. Okay. Then next property, the fourth one. So if I consider this kind of thing, del of, suppose if I put it minus sign, okay, is it any meaningful? Because this will exist at t equal to 0 only. So it is negative, positive, does not matter. If sometimes if you get del of minus t, it is same as del of t. Okay, that idea also we can get, that we have considered even function, even pulse kind of things, okay, get function, and then you will see that this is a concept of even function. But it is not that much important. And fifth one, if you are scaling delta at, that is useful, that we should write in this form, 1 upon mod of a times delta t. So that is again the concept of that one, scaling factors. Fine. The next one, time shifting, already I have showed that. So these things already I have said, del of t minus capital T, it is nothing but it's the impulse located at t equal to capital T. Small t equals to capital T. So this is impulse at t equals to capital T, nothing else, right? Now another thing, important thing we are getting, so if I take derivative of dut, step signal, then we will be getting del t. Why it is so? Because you can see that ut signal is defined as, this is 0, this is suddenly it is 1 and it is remaining 1. So this is your u of t with respect to time t. Now if you take derivative means slope, okay. So if I take this side, it is 0, so derivative will remain 0, and this side it is a constant slope and slope is 0, that's how its derivative will be also 0. But here there is sudden change. This sudden change is corresponding to its slope is 90 degree, so tan 90 is infinity. That's how its derivative of ut will become impulse, and here you will be getting one impulse. Okay, so in opposite way, if you integrate this del t dt from minus infinity to certain time t, then you will be getting u of t, step signal. Okay, and there are more applications. We will be discussing convolution, but not right now. Just we will give you the property for that. Then next property, suppose 8th property. If I consider one signal x of t, and if I take convolution with del t, we will be getting same signal xt. This convolution thing, what is the meaning of convolution? Briefly I will be discussing here, then you can understand what is the meaning of this. I have one system, this is one system, okay, it's a LTI system, linear time invariant system. The claim is that if its impulse response is given, what is the impulse response? If I apply impulse, we will be getting one response, and that response I will consider, suppose yxt is the output, so this is called impulse response. So it is a response due to impulse signal. So whenever system is applied in the system, we apply impulse signal, whatever result we will be getting, output we will be getting, that is called impulse response. And thing is that if this is known, then for any arbitrary sequence xt or signal xt, we can get corresponding output yt, which is nothing but convolution between xt and ht, and it is defined as, we'll discuss this thing in detail in next video, how to get this one. I told you that formulation, no, that xt could be written as summation of x of tau and del of t minus tau d tau minus infinity. This will play a big role. Okay, so you can see that similar form will be getting here. It will be x of tau, h of t minus tau, and d tau. This is from minus infinity to infinity. So this is the convolution. Okay. Now what I am saying that this output yt is nothing but convolution between xt and ht, where ht is the impulse response. Now in this case, I have taken convolution between xt and del t. What will happen? Will I get xt again? What is the meaning of this? So if I consider one system, just see from system point of view. What I have said, if I apply xt, and I will be getting the convolution of this and impulse response. Now if I say its impulse response is delta t, then obviously this output yt is nothing but convolution of xt and delta t. Is right? Now I am saying it is a delta t is the impulse response. Now what is the meaning of impulse response? I have said if I apply del t, that time whatever we will be getting. So I am applying delta t and my impulse response is delta t, I am getting again delta t. So I have applied delta t, I am getting again delta t. So if I apply xt, I will be getting again xt, because same thing is obtained. Output is same as input. So if impulse response is delta t, imply that input equals to output, output equals to input. So this output yt will be same as input xt. So this thing is happening. So xt convolution del t is same as xt. Okay. So we can also prove it in different way. From this definition also we can prove this one. So xt convolution delta t, by definition what I am getting, x of tau, del of t minus tau, and d tau, and this is minus infinity to infinity. Again I told you that these things, already I have discussed this one, that this function will exist at tau equal to t. So this product I can replace by minus infinity to infinity. This is your tau, I can replace by t only. Here tau is a t is a parameter. So when tau equal to t, that time this sample will be there, and that is multiplied with this impulse located at tau equal to t. Okay, so I'll put keep this thing tau 1 is t d tau. Now you can see that x of t is independent of tau, that I can take outside. So it is del of t minus tau d tau minus infinity to infinity, and you know that this area under this curve unit impulse is 1, so it is xt times 1 is same as xt. Okay, so this is very useful property. So next one, so if it is a delay kind of thing, xt convolution with del t minus capital T. Okay, that you can easily guess. So from system point of view also you can find out. So it is a system, its impulse response is del t minus t. So what is the meaning? Meaning is that if I apply del t, I will be getting del t minus capital T. That is the meaning. So if I apply xt, so you can see that what is the relation between input and output. So output is delayed version. It's a delayed version. It's a delay, capital T delay. So if I apply xt is applied, then what is the output? Its corresponding output will be simply a delayed version of that, x of t minus capital T. So that's how, if I take convolution of these two, so I will be getting a delayed version t minus capital T. So this is very useful. Okay. Now can I take one such example? Okay. So let us consider one example. So del t minus 4 convolution with del t minus 6, what you will get? Okay, so can you think about this one? So this thing I am considering as a system, and this is the input signal. Okay, the system is del t minus 6. So if I apply del t, what I will get? I will get del t minus 6. It's a delay, 6 second delay. Now if input is delayed further, input is delayed by 4 seconds further, so output will further delay, 6 second delay. So 6 second delay should be introduced. So 6 more, so delta will remain delta. So 6, it was 4 delay, 4 plus 6, it will become 10. So del t minus 10. So it is becoming del t minus 10. Basically these two will be added. So in general, del t minus tau 1 convolution with del t minus tau 2, it will become del t minus tau 1 minus tau 2. It's okay? It's fine. Now just quick one example, one more example can I take? So can you tell me this thing? Suppose if I going to consider tq and delta t minus 2 dt, this integration, what is the value? Okay, that's very simple. Already I said that. So this signal is existing only t equal to 2. So I can replace here first. So 2 to the power q, and that will be outside. It's a constant. Then remaining thing del t minus 2 dt minus infinity. This will be 1. So this is 8 into 1 is simply 8. Okay. So we are taking exactly what is happening. We are taking the samples. So this is one useful concept. So this is one TQ graph, right side, and this side could be like this. Okay, I'm not drawing. So at delta t, this is at 2. At 2, what is the value? This value is, so this is your TQ plot. So it is a 2Q means 8 height. So it is taking the samples. So f of t del of t minus tau dt, this integration, it will take the sample at t equal to tau, so you will be getting f of tau, that we have already shown. Okay, that properties I have got, I have shown these things. Where it is? This thing only, this property. So it is sampling property. So that we can say it is a sampling. We can take sample at t equal to capital T by this method. So we'll be discussing more such concept. So keep watching, and if you have enjoyed this video, just you can press a like button. That is sufficient for me. Okay, and if you enjoy this video and if you want to get more such videos in this channel, you may subscribe this channel. Thanks for watching.